All right, so those of you who have been paying attention may sort of wonder why it is that we've been talking all semester about electric and magnetic things, and then suddenly we transition to waves. And the short answer is, as we'll see, that one of the things that comes out of what we understand about electric and magnetic fields is that if you couple them in the right way, you can end up with electromagnetic waves. And so when we start talking about waves, electromagnetic waves are one of the important types of waves that we can have. So to sort of set this up, let's talk about what are Maxwell's equations. And Maxwell's equations are basically sort of the four governing equations that cover what's going on with electric and magnetic fields. Several of them we've already run across before. And so the first one, of course, is Gauss's law for electric fields. And we know that that's given by the integral over a closed surface of E dot dA, and that equals Q enclosed over epsilon naught. So what this tells us is a couple of things. One, it says that charges produce electric fields. And two is that electric field lines begin and end on charges. So that's simply, we talk about, hey, an electric field line runs away from positive charge and towards negative charge. There's also Gauss's law for magnetic fields, and notice it has the same form on the left-hand side, but it equals 0 on the right. So it says over some closed surface, the integral of B dot dA is always equal to 0. So this tells us a couple things as well. The most important being that this means there's no magnetic monopoles. So Gauss's law for electric fields says you can separate positive charge from negative charge. Gauss's law for magnetic fields says you can never separate north poles from south poles. Doesn't take your magnet, cut it up into smaller and smaller pieces, it doesn't matter. You still always have both a north and a south pole. Which means that magnetic field lines don't begin or end, instead they loop. So these are sort of our Gauss's law versions for both the electric and magnetic field. The other two basically tell us about how magnetic and electric fields change. And so the first one, of course, is Faraday's law, which says that the integral over some closed loop of E dot dr is equal to negative the change in the magnetic flux with respect to time. Now, we tended to write this as the potential, but all this is the definition of potential that happens to emphasize the electric field. So this is nothing new about Faraday's law. It's just sort of changing. So instead of writing this as an EMF, we're simply writing it as the sort of fundamental definition of what the potential difference is. Again, what does this tell us? Well, basically it says that changing magnetic flux produces an electric field. When this term is non-zero, you have to have an electric field present. Then there's the Maxwell-Ampere law. And again, Ampere's law we've dealt with. It's very similar to this one, right? It says the integral over some closed loop of B dot dr is equal to mu naught I. But one of the things that Maxwell did, and part of this is why we sort of call these Maxwell's equations, is he realized that there had to be some symmetries here. And so this symmetry of changing the magnetic field produces an electric field, he hypothesized that that's also true here, and then in fact it is. It's just that this number that's sitting out here as a coefficient in front of this term is incredibly small, which is why nobody had measured it first. So Faraday's law doesn't have that really tiny coefficient out here, so Faraday was able to see what was going on, to see that behavior in terms of how you would get an EMF as you change the magnetic field. This number is in fact so small that it wasn't until you knew that you needed to go look for it that you saw that sure enough changing the electric field also does something. And again, what it does is it says that changing the electric flux or having an electric current either one of those produce a magnetic field. Now, when you get sort of out in vacuum and you don't have to worry about this current term, then you notice that the Maxwell Ampere law and Faraday's law, again, very much parallel each other. And so, in fact, what that led Maxwell to recognize was that if you take Faraday's law that says changing magnetic fields induce an electric field, and you take the Maxwell Ampere law which says changing electric fields induce magnetic fields, putting those two things together says that if you can couple a changing magnetic and electric field together, you'll end up with something called an electromagnetic wave. So an electromagnetic wave, here's sort of our picture representation of it. So the electric field is the blue one, and it's oscillating. The magnetic field is the red one, and it's oscillating. And this gives us a magnetic wave that travels in a direction that is perpendicular to both of those fields. So if you couple these things together and change so that the electric field is changing with the magnetic field as it's changing, then you end up with what's known as a magnetic wave, electromagnetic wave. So just some four important points to emphasize in terms of electromagnetic waves. One is that the electric and magnetic fields are perpendicular to each other and they're in phase. So again, where the electric field is at a max, the magnetic field is also at a max. Two, the wave travels in a direction that's perpendicular to both E and B. Three, unlike mechanical waves, electromagnetic waves do not need a medium to travel through. Right? So we said mechanical waves, whatever kind there were. If you want to talk about water waves, it had to have a medium of water. You want to talk about sound, you need a medium of air. Mechanical waves need a medium to travel through. Electromagnetic waves don't. They don't need a medium because basically this coupled oscillation allows them to sort of propagate on their own without needing something to travel through. And then the last one is electromagnetic waves transport energy. So in the same way that any wave, right, we talked about mechanical waves, any wave is a way of transporting energy without transporting matter. Electromagnetic waves are just the same. They transport energy as they propagate. All right. So like any other wave, sort of the basic way we describe them is the same. We talk about the wavelength of the wave. We talk about the amplitude of the wave. Again, the amplitude of the wave is telling you something about the energy involved in creating it, so that's really a description of the power needed to keep the wave propagating. The period is going to be the time it takes for one oscillation. The frequency is the number of oscillations per second. So the period, the frequency, and the angular frequency are all related to each other in the way that we know about. What's special about electromagnetic waves is that this very tiny coefficient that we talked about in the Maxwell Ampere law ends up coming back in the wave equation when you describe electromagnetic waves, and it happens to correspond to the speed of the wave. And so the speed at which an electromagnetic wave travels, which we designate with this letter C, is equal to 1 over the square root of epsilon naught times mu naught. So again, epsilon naught is our fundamental constant dealing with electrical stuff. Mu naught is our fundamental constant dealing with magnetic stuff. And again, coupling this together has given us the speed of the wave. Now, many of you probably recognize that this value for the speed of the wave happens to be 3 times 10 to the 8 meters per second. We have a name for that. It's called the speed of light. So light is one of a thin sliver of possible electromagnetic waves. As with any wave, I can think about the speed of the wave is equal to frequency times the wavelength. So here, if I have the speed of the light in meters per second, frequency in hertz, the wavelength in meters, this equation also describes what's going on with the wave. And so what we can do is we can talk about light And we know that light comes in different colors. And so if the speed of light is the same for all of them, and it is, then increasing the frequency means that you decrease the wavelength. So notice as we look at these pictures, red clearly has the longest wavelength. Well, the longest wavelength means that it also has to have, if this number is larger, right? Longest wavelength means that value is larger. That means you have the smallest frequency. So your longest wavelength wave of red light corresponds to the lowest frequency value. On the other end, violet has a relatively short wavelength, which means it must have a high frequency. And so what you can do is you can talk about the visible light spectrum as going from red to violet is increasing in frequency and decreasing in wavelength as you go from red to violet. So this is just sort of, again, emphasizing that, putting some numbers with it. So our long wavelength wave, red, has a wavelength of about 700 nanometers. Short wavelength violet light has a wavelength of about 400 nanometers. That corresponds to, violet is about 7.5 times 10 to the 14 hertz. Red is about 4.3 times 10 to the 14 hertz. And so again, you can see that the violet end is your high frequency short wavelength. Your red end is your low frequency long wavelength. And so anything sort of between those two extremes, right, if it's closer to red, it's got a lower frequency, longer wavelength. If it's closer to blue, it's got a higher, or if it's closer to violet, it's got a higher frequency, shorter wavelength. Now we said that visible light is just a thin sliver of the total electromagnetic spectrum. Well, the total electromagnetic spectrum is basically stuff that runs from radio waves all the way up to gamma rays. And so here's sort of generally the major groupings that we split the electromagnetic spectrum up into. Radio waves are low frequency, long wavelength end of the spectrum. Microwaves have a shorter wavelength, larger frequency. Again, as you go up to infrared, the wavelength is getting shorter, the frequency is getting larger. Here's visible light, where again we go from red to violet. Notice infrared is the name we give for light that is just smaller in frequency than red light. Then we go from visible light, red to violet, and then ultraviolet is the light that is just larger in frequency than violet. You keep increasing in frequency, decreasing in wavelength, that gets you to X-rays. Go even farther up, that's what gamma rays are. So this is the entire electromagnetic spectrum. And again, the important thing here is that all of these forms of the electromagnetic spectrum all travel with the same speed. They all travel with the speed of light. So sort of here's just a simple chart kind of organizing this information again. Again, you go from radio on this end to gamma ray on this end. The wavelength has gotten shorter as you move to the left. The wavelength gets longer as you move to the right. The frequency gets higher as you move to the left. The frequency gets lower as you move to the right. And so sort of the typical sizes of the wavelengths that you're dealing with, well, radio waves can have incredibly long wavelengths. You can have something on the order of a football field, even longer than that. Microwaves basically take you from something about the size of a baseball down to something about the size of a pinhead. Infrared roughly takes you from stuff that's about, stuff that we think of as tiny that we can see, all the way down to things that we know that we can't see without using some sort of microscope. Then visible, that's stuff that's even smaller than bacterium. But once you go beyond that, now you're talking about wavelengths that are on the order of proteins. X-rays get you into wavelengths where you're talking about on the size scale of atoms. And then gamma rays are even smaller than that in terms of their wavelengths. So they're on the scale of nuclear sort of things. So what happens then is that these different forms of light, right? You need a different detector to see each of them, but they tell you something about what's going on within a certain picture. So you see sort of here two pictures of exactly the same thing. Visible light over here, infrared light over here. And what you notice is, here we see colors, the guy's glasses, they're translucent, you can see through them. The trash bag is opaque, you can't see through it. But when you look in infrared, right, infrared is basically the way that which we see heat. And so that's why the hottest spot in this infrared image is actually his face. His clothing is keeping in some of that body heat so it doesn't radiate nearly as high. You'll notice that his glasses, they're not translucent. They're actually opaque in infrared. Infrared light doesn't penetrate those glasses. But now you can see through the trash bag. So again, given the properties of the material that make up the trash bag versus make up the glasses, right, you can now see through the trash bag. You can't see through the glass in his lenses. So this is just sort of, again, just an idea of how different wavelengths of light can give you different information about what's going on. If we look on a grander scale, this happens to be our next door neighbor, so this is Andromeda. And we're looking at it in 5 different chunks of the electromagnetic spectrum. So here down in radio, basically what you're seeing is the cold gas that's largely distributed throughout the arms of Andromeda. When you come up in the infrared, what you're seeing is the dust that's sort of concentrated in the center of that gas. Visible light, notice that some of the places that are showing up incredibly bright here are actually dark spots here because that dust, the visible light, can't penetrate that dust. So the dark lanes that you see here actually correspond to the bright things that you see there because, again, they're both the dust. This is dust in absorption, so it doesn't let the light through in the visible. This is dust in emission, so you do see the light in infrared. When you get up into ultraviolet, now what you're starting to see is really just the hottest stars. So this is, you're seeing cooler stars and dust here. Here you're just seeing the hottest stars. And then when you get all the way up to X-ray, you're really only seeing high energy processes. And in fact, this really, really bright spot in X-ray sitting at the center of Andromeda happens to be the supermassive black hole that sits at the center of that galaxy. So again, all this is just sort of emphasizing that with electromagnetic waves, there's a lot going on. There's many different regimes of the electromagnetic spectrum that we can look at. Our eyes are a detector that sees invisible. But we have built detectors to see in all these other regimes. And so this is just sort of, again, emphasizing light as a wave that then we'll come back and talk about in terms of, reconnecting light as a wave to the interference patterns that we've been studying last couple of days.